Hello, everyone, again. Let's proceed with the practice exam number 2 for the Physics 209. So let's try to run through that. From a much earlier exam back in fall 2019. And in aggregate, the 3 exams will comprise a decent review for Physics 209 final exam. In addition to the 3 other exams from a non-calculus version of the same type of course, those 3 exams and what I went through regarding those are also good practice for the final exam for Physics 209. As we said last time, I went through 3 essential practice exams for non-calculus treatment of mechanics and heat, which comprised a good review for the final exam for the non-calculus treatment of physics for a particular final exam. In short, if one were studying for a final exam for non-calculus treatment of mechanics and heat, those 3 exams I did for Physics 120 at the school we're at, those 3 exams would comprise a good review for the final exam for non-calculus treatment of mechanics and heat. These current exams, the 3 of them comprise a good review for the calculus treatment of the physics associated with mechanics and heat. The final exam for the calculus treatment of mechanics and heat, these particular exams comprise a good review for that type of subject matter. Both sets of exams, the non-calculus 3 exams and the calculus treatment 3 exams, those two sets of 3 practice exams each, shown in 3 videos each, 6 films total. Those 6 films comprise a good review for much of what you would see in non-calculus mechanics and heat, and would help you in a final exam for non-calculus mechanics and heat. And they would also help you in calculus-based treatment of mechanics and heat, and for a final exam pertaining to that. So there's 3 films in the non-calc realm, I guess you could say, that I've already talked about, and 3 films now in the calculus realm. Very many of the problems aren't even calculus-type problems, but they're a little more difficult than what you'll see in the non-calculus version of similar content. All these films can help in both subject matters, non-calculus and calculus version of mechanics and heat. So we've said that. We can do it. Let's look at exam number 2. Let's go through 1 through 25 on that. I'll try to go relatively quickly, guys. It's somewhat hard to do sometimes, given the amount of content. To explain it is more difficult than to actually do it sometimes. So let's see what we can do, and we'll take it from there. For number 1, from exam number 2, and again, guys, I want to be careful with the audio here. I've had some audio issues that I'm largely at fault for, so I'm trying not to have that be an issue any longer. Okay, so let's take a look. For exam number 2, let's look at problems 1, 2, 3. See how many there are. 1, 2, 3 pertaining to Kepler's laws. Now, so 1, 2, and 3 regarding Kepler's laws, and we're talking about, the period, the square of the period is directly proportional to the cube of the radius of the orbit. So let's see what we can say here. So what we're saying here is Now, we've proven this by equating, and we're not going to really go there completely, but equating the centripetal force with the force of gravity. We've played some games with that. mv squared, the mass of the object that is in orbit. Here's r, and here we've got g, a very massive object, big M, and this is the object that's in orbit once again, m. These are the same m's, and this is r squared. So this is the force of gravity. You're equating it with the centripetal force. When you do that, if you treat A as approximately equal to the radius, so we'll say that, if the radius is A, the square of the period, the C is a constant. The square of the period is directly proportional to the cube of the radius. The square of the period is directly proportional to the cube of the radius of orbit. So we have that right there. Let's continue to look at this and see if we can play the game. Number one, two identical planets. And some of this might be a repeat of things I had done with the non-calculus practice exam. So don't worry about it if it is. I mean, we'll see it again, I guess. For number one, two identical planets, P1 and P2, orbit a star in concentric circular orbits in the star's equatorial plane. P1 has an orbit of radius, A1 is 20 astronomical units, and P2 has an orbit of radius of A2 is 30 astronomical units, and T2 has a period, T sub 2 is 30 years. What is the period of T1? Okay. A little easier done than said. This is kind of the bread and butter of where you're going, guys. You're using this throughout the process. I have this I'm sure I have this on film somewhere, having actually derived this. In person, I have derived this as well for my students. So we're getting this conclusion from what we had said here. We get this excellent conclusion right here. What can we say about it? Well, dealing with that, we'll say, okay, I don't know what T1 is, so I don't know what T1 squared is. C is just some constant. A is the cube of the radius of orbit. T is the square of the period, the amount of time it takes to go all the way around in the orbit. So what we have here is A1, right? And A1 they already kind of gave us in terms of the astronomical units, you guys. Again, proportions are so huge to be able to solve problems like this. It can almost not be emphasized enough. You've got this. The other one is telling you the period is 30 years. Square it. C is C. If it's the same system, the C is the same. If it's not the same system, if capital M is a much bigger or much smaller quantity than what was present somewhere else in some other system, we are talking about a different C being present. But when we're talking about the same system, the C is constant to both, whatever that might be. They are telling us, okay, I think it said, yeah, they said 30 and 30. So 30 years, 30 astronomical units. Right, 30 years, 30 astronomical units is what it must be. If you've got this right here, you're just comparing. Comparison's a big thing. Ratios are a big thing. When you do this, take this divided by that, and you got T1, the ratio of squared quantities. We'll leave it as is. We got this. Divide these two, the C's cancel, and you've got this. Forgive me, this should have been squared, this should have been cubed rather, and then these are cubed. That's cubed, and that's cubed. Okay. Wheel and deal with this, guys. We got T1 squared is 30 squared times this ratio, 20 to the third over 30 to the third, 20 to the third over 30 to the third. The ratio of exponentiated quantities is the exponentiation of the ratio. Again, you have to have the mathematical dexterity to do a lot of things, folks. Okay, that's really the goal We're doing a lot of this stuff. The ratio of exponentiated quantities. The ratio of exponentiated quantities is the exponentiation of the ratio. Okay. Whether it's good or bad, I don't know. Maybe that's a good move, maybe it isn't. I don't know. Maybe I did it. Maybe I shouldn't have, because the cancellation might have been a lot easier had I not done that. Make a long story short, I mean, yeah, you'd almost want to put these back in here, but okay, well, at least we have the dexterity to do it if we need to. We got a 30 on the bottom here. There's 30 to the third, 30 to the second. They cancel. I just got 30 right here. And then this right here is 8,000. And then you square root each side, and you should get T1 is 16.33 years. Fantastic. All right, that's one. Two, you're using the same equation. I mean, this is a big one right here, guys. Once you got to here, it's important for us to have this under control. We got this. We're using it for 1, 2, and 3. 2 is saying two identical planets, P1 and P2, orbit a star in concentric circular orbits in the star's equatorial plane. We had that happen earlier in number 1. Same setup. P1 has an orbit of radius 10 AU, astronomical units, and T1 15 years. P2 has an orbit of radius A2 in period 20 years. What is the radius of P2? Make a long story short, again, we're staying with this. They're telling us, we'll just take, here's T2, we'll square it. T1, just be careful, that's all. What does that mean? Well, T2 is 20. A2 is unknown. T1 is 15. And A2 is 10. All right, let's make sure. I mean, these numbers are right. I just want to make sure I'm calling them the same name here. Yeah, A1 is 10. A1 is 10. T1 is 15. A1 is 10. T1 is 15. Forgive me 1 second here, guys. Yeah, A1 is 10. T1 is 15. All right, let's just play the ratio game again and see what happens here. Divide both equations. The ratio of exponentiated quantities is the exponentiation of the ratio. The C's cancel. You got this. A3, A to the 3. Or this guy. Well, this guy to the third is 1,000. Let's just cut to the chase, I guess. Let's do the math. Let's multiply by 1,000 on each side. And you got A2 to the 3 is basically, I don't know where you want to stop on this stuff, guys. You go here times 1,000. Okay, well, let's figure that out. A2 to the 3. There's a lot here. I mean, so we do a lot, I guess. 20 divided by 15 is 4/3. Square that, you got 16/9 times 1,000. That's what this is going to be equal to. When you're done with that, you know, you get to here. Let me get the cube root of both sides. I don't know how visible this stuff is sometimes, guys. I'm a little apprehensive. The cube root. So you take the cube root of both sides. The cube root of a sub 2, the cube root of a sub 2 cubed is a sub 2. The cube root of this is square this first. You got 16 over 9. Get its cube root, multiply it by the cube root of 1,000, which is 10. At the end of the day, you get 12.11 AU. A sub 2 is 12.11 AU for problem number 2. A sub 2 is 12.11 AU. Okay, that's 2. 3, two identical planets, again, P1 and P2, orbit a star in concentric circular orbits in the star's equatorial plane. That introduction is common to problems 1, 2, and 3, which is good. It kind of sets us in a very predictable manner as to where we need to go. P1 has an orbit of radius A1. That's planet 1 has an orbit of radius A1 and period T1. And P2 has an orbit of radius A2 and a period T2. Given that A sub 2 over A sub 1 is 1/8, what is the ratio of periods T sub 2 over T sub 1? Okay, so they're basically telling us let's figure out how we want to do this, actually. Okay, so we're saying A2 over A1 is 1/8. Okay, so A2 over A1 is 1/8. They want to know what T2 over T1 is. That's the question. Basically, as we did over here, guys, if you're gonna, if you want to look at, and what are they asking here? I think they're asking T2 over T1. So I kind of went the wrong way on that one. Let me go here. T2, T1. Okay, let's see what we got here. Forgive me here. I might as well use some of the board space, I think. T2 squared C A sub 2 cubed T sub 1 squared C A sub 1 cubed. Let's use this. I mean, let's come over here. If I'm getting ratios, let's get the ratios. Let's take it from here. Take this divided by that. That's going to be equal to this divided by that. The C's cancel, and it looks kind of interesting. What happens is you get T2 over T1. T2 squared over T1 squared is T2 over T1, the quantity. The ratio of two, if you get the ratio of these two exponentiated quantities, the ratio of these two exponentiated quantities is the exponentiation of the ratio. The ratio here, the C's cancel, the ratio of these two exponentiated quantities, give me this. Now, wait a minute. That's all right. We're pretty close to it now. A sub 2 over A sub 1 is 1/8. This, A sub 2 over A sub 1 is 1/8. 1/8 right here, 1/8 cubed is equal to T sub 2 over T sub 1, that ratio, squared. This is where it's happening. So, this will get us there. Maybe not easily, but it'll get us there. If you square root both sides, you're there. It's as simple as that. And that'll give you that. So if you want to get T2, T2 over T1, why don't you square root both sides? Square root this. You got T2 over T1. And square root this, not cube root, because you're getting rid of the 2 here. Earlier I was doing a cube root, right here. That's a different story. Here we're doing a square root of 1/8 over that. Now, whatever that may happen to be. There's a number of ways I can write this. I don't know that I want to get too adventurous with this. That's the third power. Take 1/8. Take it to the third power, get an answer, then get the square root, and you're done. Take 1/8 and take it to the third power. That's 512. That's 1 over 512. The square root of 1 over 512 will be what this ratio is. It's as simple as that. It comes out to 0.0442. And some of you may already see this in other places, guys. It's hard to know. Got enough problems. Some of them have a repeat on them, but it's nothing wrong with looking at this stuff and just knowing what you're doing. You got to look at it more than once. There are worse things in life, I guess. 0.0442. And that's number 3. That's number 3. You see here, guys, I'm always apprehensive about the audio now. I got bit once. Okay, here we go. We're looking good. Number 4, the horizontal surface on which the block slides is frictionless. The speed of the block before it touches the spring is 50 meters per second. How fast is the block moving at the instant the spring has been compressed 30 centimeters? K is 1,200 newtons per meter. All right, so we'll see what's going on here. We'll talk about it. Excuse me, guys. I got to kind of make sure these erasers are going to work for us. Okay, so let's see what we have here. All right, guys, they're saying basically this is a classic conservation of energy type problem. And we're going to treat it as such. I mean, you got this. It's a frictionless surface. There is a spring. There's a spring. And it's got K as the value of its spring constant. And there's a 2 kilogram mass. 2 kilogram mass moving velocity, magnitude velocity v to get this done. The spring constant, K, the spring constant is 1,200 newtons per meter. The speed of the block before it touches the spring, before it's engaged with the spring, is 50 meters per second. And, the mass is 2 kilograms, as we said. And put it here, I guess. 2 kilograms. And the amount of compression that will take place is 30 centimeters. Now, there we got to be careful. X is the amount it compressed. 30 centimeters, every centimeter is 1/100th of a meter. So 30 times 100th is 30 hundredths meters. Just move the decimal place 2 places to the left, 0.3 meters. You want to make the units agree, you guys, and we've done just that. Now, so a lot can be said. Let's say it. Energy is conserved. I don't want to get too adventurous even with that statement, but energy is conserved. Energy initial of the system equals energy final of the system. The initial energy of the system is the mass moving with some kind of initial velocity. The initial velocity is this. So we'll call this V sub I. 1/2 mass times initial velocity squared. Then there is the work done on the spring. And then there is a loss of kinetic energy. So now there's a new final velocity, VF. They want to know the final velocity. This is what is going to get you there. You're going to solve for V sub F. It's as simple as that. It's as simple as that. Subtract. You can do a whole lot here, guys. There's halves all over the place. Multiply by 2 on each side of the equation. Subtract kx squared on each side, and you got, so let's see here. You got m vf squared. You multiplied by 2 across, you multiplied both sides of the equation by 2. You subtracted what remained on this side of the two things on this side of the equation. You subtracted kx squared on each side. You got to here. Divide by m on each side. Divide by m on each side. It's a big move. It's a big move. When you get to here, square root both sides. Okay. Pretty major moves there. Forgive me, if you square root both sides, you got this. Plug in everything. This is 50. Square it. 2,500. This is 1,200, and this is 2. 1,200 divided by 2 is 600. This is 0.3. Square it, that's 0.09. 0.09 times 600 is 54. 2,500 minus, let me just make sure I did it right, 1,200 divided by 2 is 600. 600 times point, it's 0.09. It's going to be 9 times 6, 54. 2,500 minus 54 is 2,446. The square root of 2,446 is 49.46 meters per second. Absolutely. So what do they say here? What are we going to say about it? Number 5, what is the momentum of the block at maximum compression of the spring? At x equals 30 centimeters. What is the momentum of the block? That shouldn't be too bad. The way the question's asked could be kind of a little difficult, but let's see what we can do here. The final momentum, the maximum compression of the spring is 30 centimeters. So that's 30 centimeters is 0.3 meters. Well, we already found out how fast it was going. Basically, PF is mVF, and that's it. That's how it's going to work. So you get P sub F is the mass of the block. So let me think here, guys. The mass of the block is 2 kilograms. 2 kilograms times 49.46 meters per second is going to be 98.92 kilograms meters per second. This might have been a round off, so the number comes off a little, comes off a little differently. 98.91 kilograms times meters per second. It's that momentum, right? We know what momentum is, but you got to get it right to get the problem right. Right? That's number 5. Number 6. Number 6, 2 automated vehicles. A 1,000 kilogram car traveling at 60 meters per second collides directly head-on with a 3,000 kilograms. So there's a 1,000 kilogram car traveling at 60 meters per second. It collides directly head-on with a 3,000 kilogram truck traveling in the opposite direction at 40 meters per second. And they stick together. They both are traveling on the same line of motion, but opposite directions. What is their speed right after they stick together? A classic conservation of momentum problem, folks. So what happens here is you got like this. Well, the initial momentum is one's doing this, the other one's doing this. You've got to respect the signs. They're going in opposite directions. So that has to be accounted for. This is a vector quantity, like we mentioned up here. When they stick together, whatever that vector is going to be, the sign respects that. It'll show that. So you got this. If you solve for V, you're good to go. V is going to be divide by this quantity, M1 plus M2 on each side, and you get V is equal to M1 V1 plus M2 V2 you got this. This is really the thing. Okay, good enough for me. Let's do it. I mean, this should be enough. We can probably walk through it just putting the numbers in there, and we should be okay. And I have this on the PDF pretty. You got to call one of them negative, and you got to call the other one positive. It doesn't matter which one you call which. just get an idea, well, the direction that the truck is moving is positive, the direction that the car is moving is negative. You can say that if you want, and let's say that in fact. The car is in the negative direction. It's 1,000 kilograms times negative 60. Here, the truck is 3,000 kilograms times positive 40. Let's see what that means. What's 1,000 times negative 60? Negative 60,000. What is 3,000 times positive 40? That is positive 120,000. Positive 120,000 and negative 60,000 is positive 60,000 up here. Positive 60,000 divided by this sum, this is 1,000, this is 3,000, that's 4,000. 4,000 divided into positive 60,000 is 15. And it came out, 15. The result is 15 meters per second. And you can see this in the PDFs that I have as well, guys. This is important to note. The direction in which the truck was heading is the direction in which the amalgam of the two after the collision, that is the same direction in which the amalgam is going to be moving. They're going to be moving in the direction in which the truck was initially moving. It's a positive 15 meters per second. It would show, the mathematics would show if you were respecting the signs like we did. It would show if it was going to be a negative or a positive. It showed. That is what that is. Let me see here. So that's that. That's 6. That's 6. For 7, it relates to number 6. Here's 7. Here's problem number 7. Here's problem number 7. In problem 6, what is the amount of kinetic energy lost right after the collision, right after they stick together? How much kinetic energy was lost? It's an interesting point. Well, let's do this. I mean, initial kinetic energy minus the final kinetic energy is going to be equals the loss of kinetic energy. We're assuming there's a loss of kinetic energy here. Momentum's conserved. Kinetic energy is not necessarily conserved. So this is the reality here. Let's figure out what it is. Well, one of the cars is 1,000 kilograms. One half mass. You know, what is kinetic energy, guys? I mean, kinetic energy, what we're doing, generally speaking, kinetic energy is 1/2 mass times velocity squared. We have a situation initially that there is a 1,000 kilogram truck, 1/2 mass, going at negative 60. When I square that, that becomes positive, so that's not a problem. There is the other one, which is 1/2, 3,000 truck. This is a car, this is a truck, and this is at 40. We'll square that. That is initially what's going on. I sum the two kinetic energies. This is the total kinetic energy of what is going on. Minus what? Well, minus the fact that together they are stuck together. Here's 1,000, here's 3,000. That's 4,000 is the mass that we're talking about now. And that mass in total is going at 15 meters per second. That's all you got to do. Determine this, determine that, add them together, and subtract what this determination is. It's as simple as that. When you do that, you are getting, the end of the day here, you're getting it's a lot of kinetic energy. 3,750,000 joules have been lost. Where'd it go? In heat, in sound? Didn't get lost completely, but it's just, there's no kinetic, that kinetic energy This much kinetic energy went into other kinds of energy, thermal energy. It's also equal to 3.75 megajoules. Okay, so okay, sounds pretty good. Again, they wanted the answer in megajoules, and you have to know that mega means millions. And that's how you get the answer. So that's what we're looking at. All right, guys, let's go to number 8, and we'll take it from there. Okay, everyone. Just coming right back here. Let's look at number 8 and proceed from there. Number 8, a force of capital Fx equals 60x squared e to the negative 2x to the third in newtons. So a force capital F of x equals 60x squared e to the negative 2x to the third in newtons, acting only in the positive x direction, acts on a 5 kilogram object as it moves from the origin to the point x equals 10 meters on a frictionless horizontal surface. How much work is done by the given force during this displacement? Essentially, guys, again, it's a classic calculus problem. Now, this is in the calculus realm now. F of x, big F of x equals 60x squared e to the negative. Forgive me, let me just start that over. Capital F of x equals 60x squared e to the negative 2x cubed. That is, assuming all the units are going to work out for us, they want to know the work that's done. Well, work generally, work is the integral associated with work, and that's going to be a force function going through a distance, something like that, and with the appropriate limits. With that in mind, they're telling us this is going from 0 to 10 meters, and we're assuming everything's in the quote-unquote right units. So if you got something like this, let's talk about it. They said it was a 5 kilogram mass, but that's not really what's going to win the day. This integral right here is going to make it all happen. And this is basically what you're doing here, and then later on, if we need more specifics, perhaps the fact that we're dealing with the 5 kilogram mass is going to be significant. From 0 meters, the origin, 0 meters to 10 meters, force times dx. So you got this. Here's the force, 60x squared e to the negative 2x to the third dx. The integral is itself pretty fascinating. We look at it, and let's see exactly what we could say about it. So we're looking at this. Let's see exactly where we want to go with something like that. I guess you could say there's an easy way and a hard way on this, on something like this. You could take, let me try to think here. Let me take kind of look at it. I mean, we could, there's a number of ways you could go here. You could you kind of guess the integral in the sense that, okay, if you're saying this is the answer, how do you know it's the answer? Well, let's do this in pieces, I guess you could say. I'm saying that right there is the integral of all this without going about the limits of what's going on there, guys, without talking about the limits and stuff. Well, okay. Okay, sure. Why? How? Can you at least confirm it's true? Well, we'll confirm it's true, and then let's actually prove it. If this is the integral of that, let's not worry about the limits of integration or anything. Just, get rid of the limits of integration, just integrate this. What's the antiderivative of this? Well, if you were to take the derivative of this, you'd get negative 10 by the chain rule. You'd get e to the negative 2x cubed times the derivative of this, which would be negative 6x squared. And negative 6 times negative 10 is 60. This is x squared. This is e to the negative 2x to the third. And you get the item that was being integrated. So if you guessed this out of nowhere, you'd be right. That is the antiderivative. And that is the integral before we put the limits in on the whole thing. Yeah, that's all well and good, but how'd you get there? Well, this is the truth regarding this. We just verified it doing this. The way you could do it is you could kind of say, okay, treat negative, it's a little more detail than what I showed in the notes. I'm surprised I didn't show more detail, actually, to be honest with you. But okay, so it's confirmed that's a good way to go. Great. If you happen to guess it right, you can take the derivative of it and certainly see that this item right here is what you get when you get the derivative of that. That's all well and good. So what? How would you get it? Well, how about you take the negative 2x to the third and call it u. Negative 2x to the third. And then du dx becomes negative 6x squared, which means du becomes negative 6x squared dx. And you could pull a negative 10 out of there. So here's what you could do. Let me take 60 x squared. Make sure that my audio is okay, guys. Okay, here we go. I'm all right. 60x squared e to the negative 2x to the third. 60x squared e to the negative 2x to the third. You got that. Let me not put the limits in there. Let me pull a negative 10 out of there. Let me pull a negative 10 out of here, leaving me with a negative 6x squared. Whoa, that looks like something. Forgive me, this should have been dx. So you got the negative 10 here. The negative 6x squared dx, negative 6x squared dx is the du. So you got negative 10, negative 6x squared dx is du. This is a u up here. This is e to the u. If you integrate this thing, you got negative 10, you just did the integral, e to the u. Yeah, absolutely you do. So that right there so it comes out to that, which means this becomes negative 10. Let's have a look. Yeah, there it is. I mean, it's staring me right in the face, and for some reason I'm afraid to look at it. Here's negative 10. E to the u is e to the negative 2x to the third. You got it. Didn't we guess that was the result? Right up here. We guessed that was the result. Let me get more chalk, guys, really quickly. That's it. I mean, confirmed. Negative 10 e to the negative 2x to the third. That's what we said. So that is what the integral is. So what happens is that integral is negative 10 e to the negative 2x to the third. There it is. We got it. That's the. I'm surprised I was so cavalier in the writing of it, but there it is. I mean, earlier I didn't really. It's not really shown on the PDF very rigorously, but now you're going to do it here. You're going to do that. You're going to evaluate. You're evaluating this between these limits, and that's going to be the total work. So anyway, that's interesting. That's a pretty fascinating, fascinating conclusion. I mean, yeah, the background in calculus, it's easy to miss it, even with the background. All right, let's go. See where that's going to be. Well, W is going to be, the negative 10s happen in both places, so put it right there. You can put a 10 in here, a 10 right here for x. 10 cubed is 1,000 times negative 2 is negative 2,000. So that's e to the negative 2,000, which is tiny. Now you can put a 0 here. 0 cubed is 0. 0 times negative 2 is 0. E to the 0 is 1. Minus 1. This is pretty close to 0, you guys. 0 minus a negative 1 is negative 1. Negative 1 times negative 10 is 10. The answer should be a little less. So negative 1 times negative 10 is 10. The answer should be a little less than 9. But you know what? It's close enough. And they're saying this. There it is. That's number 8. Number 9, in problem 8 above, if the 5 kilogram mass. Now we're going to use the 5 kilogram mass. We didn't need to use it. We did not need to use the 5 kilogram mass initially. We just used force times distance. We were fine. We didn't have to use the 5 kilogram mass. Could have been a 5,000 kilogram mass, a 5 million kilogram mass. Doesn't matter. The work is the work. Now how fast it goes does depend on the mass, I guess you could say. But initially we did not need to use the mass for problem number 8. For problem number 9, we will. For problem number 9, it says in problem number 8 above, if the 5 kilogram mass is initially at rest and on a frictionless horizontal surface, then what is the speed of this mass at the instant it is at x equals 10 meters? At x equals 10 meters, you will have done 10 joules of work on it. And it's all kinetic energy. It's not going uphill. To our knowledge, it's not going uphill. Didn't tell us that. Kinetic energy, it's 1/2 mass v squared. Now here's, if you don't have calculus, this you can figure out. If I told you you got 10 joules of work done, now I don't care how we did it. This is more the calculus issue of it. For those of you not taking calculus and you're not in the calculus-based class, you got to be in a calculus-based class, then I will ask you this, okay? But if I told you just 10 joules, that's 10 joules of kinetic energy. All that work that we did went into kinetic energy. It's 10 joules. Half is a half. The mass is 5. I don't know what V is, but the rest is algebra, and it's pretty simple algebra. You multiply by, you multiply by 2 on each side. Divide by 5 on each side. Square root each side. Two meters per second. Absolutely. That was 9. 10. In problem 8 above. In problem 8 above, what is the average force exerted by capital F of x equals 60x squared e to the negative 2x to the third? Capital F of x equals 60x squared e to the negative 2x to the third on the 5 kilogram mass during the displacement from 0 meters to 10 meters. What's going on here? Well, I just told you what the work was. For all intents and purposes, the work done by this very interesting mass, as we said, and here, this is what was given to us initially. So very important in that regard. It gave us this initially, you guys, and that's good enough, So we've got that. I don't know how good this shows up sometimes, guys. I'm a little apprehensive how I write stuff. All right, so we got this. What is the average force? If you do that integral and divide it by 10, you're done. You're basically doing the mean value theorem. If you're taking that function, f of x, and integrating it, taking that function, f of x, and integrating it from a to b. Well, the average value of the f of x function, average value of the force, the average value of the force is that integral divided by the distance traveled. Look, basically let's make it simple. Let's find out what the work was, and let's divide it by the distance, and we got the average. The work that was done, this integral right here is the work. So in a sense, you're getting work divided by b minus a. Well, b is 10 meters, a is 0 meters, 10 minus 0, and the work that was done. It was 10 joules of work. You ran from 0 to 10 meters. It's a 10-meter run. Divide that, you got 1 Newton. You're done. You're done. For number 10. So, let's see what we can do here. Do I have room? I might. Get 11. I'd like to maybe give myself a little more room for that one. It's not that bad. Not bad at all, but you got to draw something. So, all right, guys. Let me start this up real soon. Let me erase some of this stuff, and we'll take it from there, and we'll start it again. We'll start at number 11. Okay, folks, let's keep going.
We got number 11. How much work is done by a very strong person pushing a 100 kilogram object up a 30-degree incline at a constant speed of 4 meters per second for 20 seconds? Okay. Well, that's interesting. There's a number of ways you can do it. If the person, how much work is done? Well, I tell you what, we can look at it a couple ways. Let's see what we want to do about this. How much distance up the ramp was accomplished? For some reason here, I wrote a number that looks a little outrageous, to be honest with you. I don't even think it's true. Yeah, I don't even believe this. I wrote something I maybe should not have written. Okay, let's go. Let's see what's going on. I think I did have to correct this. So I do have this corrected. I think I do have this corrected somewhere, guys. I think what is in the actual, this particular PDF, problem number 11, there may be an issue. Let me do it correctly. I wrote a distance. Look, let's put it this way. The person's walking, running, whatever they're doing. The person is moving at 4 meters per second. 4 meters per second for 20 seconds. What's 4 times 20? 80. I wrote down 800. I don't know how that happened, but I did. So don't do that. Let's actually look at this. How much work is done by this very strong person? They're going 4 meters per second for 20 seconds. They went 4 times 20. 4 meters per second for 20 seconds. 4 times 20. They went 80 meters up the ramp. From there, we're going to figure out what's going on. I think I have a correction to that as well that I'll probably attach to all this. I have attached somewhere. But let's, in the meantime, just be aware of that. The person is doing a lot. They are here. Theta is 30 degrees. They are going a distance d this way. Let's see how far they went. And while they do that, they went a height h. And that's what's going to rule the day. The work done, there's a number of ways we can do this. I don't know if I want to show you those number of ways right now. Let's just do the way that's probably easiest. That's one of the number of ways to do it. That's probably the easiest. The work done is the force moving through a distance. The force moving through a distance is picking up a mass m under the gravitational field g, mg, that weight moving through a height h. That's that. If you get that, you're there. The person is going 4 meters per second for 20 seconds. Don't look at what I wrote. It's 800. I have no idea where that came from, but other than I did it wrong. That's 80. D is equal to 80. Now, can I ask you a question? H over D, opposite over hypotenuse, is the sine of theta. Multiplied by d on each side, d sine theta is h. D is 40. The sine of 30 degrees, theta is 30 degrees. The sine of 30 degrees is 0.5. The mathematics here, 0.5 times 40, h is 20 meters. Time out. My mistake. Yet another mistake. Okay, this should be okay. We said that the distance is 80. Right, it is. Okay, so yes, right here, in fact. Distance is 80. H is equal to 80 times the sine of 30 degrees. The sine of 30 degrees is 0.5 times 80. H is equal to 40 meters. The mass of the object is 100 kilograms. G is what we know it to be, 9.8 meters per second per second. Multiply 100 times 9.8 times 40. And you're there. Let's see. 100 times 9.8 is 980. 980 times 40. Let's see. It's 800 short of 40,000. Let me just, yeah, it is. But let me just confirm that. If this is if m is 100, if m is 100, if m is 100 and g is 9.8 and h is 40, 100 times 9.8 is 980. 980 times 40, right, is 800 short of 40,000. The numbers I got here are off by a factor of 10, guys. This is where it's at. This right here is the same as 39.2 kilojoules. They mean the same thing. Yeah, don't know where I got what I got, but even the possible answers are themselves wrong. So please note number 11. I think I did number 11. I did it again, and I do have it in notes, and it will be in the notes for you that there has to be a correction to it. Everything's off by a factor of 10. If B would have been 39.2 kilojoules, that would have been the answer. So anyway, unfortunately that happened. This is the correct answer. This is the way to do it as we study for the final exam. Okay, so that's that. That's number 11. Number 12, a 100 kilogram object falls vertically downward in a viscous medium at a constant speed of 15 meters per second. Constant speed. How much work is done by the force the viscous medium exerts on the object as it falls 200 meters? Well, that's a lot of viscous medium there. It's 200 meters, at least 200 meters worth of a fall. As it's falling at a constant speed. If something falls at a constant speed, or at no speed for that matter, there is no unbalanced force on it. This is a constant speed, so there's no unbalanced force on it. Whatever the force of gravity is on this object, that is the same exact amount of force in an opposite direction exerted by the viscous medium, because this thing is not accelerating or decelerating for that matter. Whatever the weight of the object is, that same amount of force is being exerted in the opposite direction by the viscous medium, kind of like a parachute. So that force that it's exerting is opposite to the motion. So as this thing falls, this thing's pushing in the opposite direction. It's 100 kilogram object. So what we got here is basically mgh, but it's got to be negative because the negative mg is what the viscous medium is exerting. So it's kind of interest in that regard. It's opposite to what the weight is, but equal magnitude. So let's see what they're saying here. H is going in the opposite direction. The displacement takes place in a direction opposite what the force of the viscous medium is. So it's 100 kilogram object, 9.8, and it's opposite what the displacement is. The displacement is 200 meters. That's pretty fascinating stuff. Well, knock out knock out the mathematics, and let's see what happens. And there it is. That's 12. Um, "13. The only force acting on a 2-kilogram body moving along the x-axis is given by capital F of x equals 5 e to the negative 3x newtons, where x is in meters. If the velocity of the object at x equals 0 is 0 meters per second, how much work is done by the force as the object moves to x equals 30 meters? How much work was done from 0 to 30? See that one more time, guys. The only force acting on a 2-kilogram body moving along the x-axis is given by capital F of x equals 5 e to the negative 3x newtons, where x is in meters. If the velocity of the object at x equals 0 is 0 meters per second, how much work is done by the force as the object moves to x equals 30 meters? It's along the x-axis. Nothing other beyond that. How much? And everybody's going along the same line of action, I guess you'd say. The displacement and the force are all in the same direction. There's 0 degrees between them. How much work was done? How much work was done from x equals 0 to x equals 30? Okay, it's a pretty neat problem. Essentially, what you're doing is, we'll take it. Again, it kind of plays the way the other problem played out a little bit. Let's see here. So for 13, the work done is force times distance. And you're integrating it, which kind of makes it really interesting. From x equals 0 to x equals 30, the force is like this. The force varies like this in relation to x as you go from x equals 0 to x equals 30. This is the force, and you just keep integrating. You integrate with respect to dx, and you figure out what's going on here. Well, here, it's a little easier integral than what we had the last time. The way you're looking at this thing would be, okay, how would you get a derivative that actually got you this? Give me a number. Give me a function whose derivative gives you this. Well, how about e to the negative 3x, get its derivative, which is negative 3 times e to the negative 3x, and let me see here. The 5 is in there for the ride. Negative 3, when you get its derivative, so let's see here. You would basically take 5 over negative 3, e to the negative 3x. It may not need to go more than that. Let's just see how that works. If I take the derivative of this, I get e to the negative 3x, timed by the chain rule now, e to the negative 3x. Don't worry about this right now. We just want to get the 5 right here. We got to get the 5 right here. We won't worry about it. I'll leave the 5 over here. I think I might have covered it. E to the negative 3x, its derivative is e to the negative 3x times negative 3. Negative 3 times negative 5 over 3 gives you the 5. That's it. You got it. This derivative gives you this. The derivative of this quantity, the derivative of this function, gives you that function. You're done. You go here, you go 0 to 30. Here we go again. Wonder how this is going to play out. Should play out okay. If I knew how to write, it would play out okay. Let me see what we got here. All right. Let's do it. This would be -5/3. It's happened in both places. Here we go again. Start up here. Put the 30 right here. That's E. Put the 30 right here. 30 times -3 is -90. That is tiny. It's really close to 0. Put the 0 right here. 0 times -3 is 0. E to the 0 is 1. Here we go again. This is about 0. This 0 minus 1 is -1. -1 times -5/3 is +5/3. 1.67 roughly. Let's see. Yeah, right about there. It's 5/3 joules. Okay, so and there you go. Not bad. See how it continues to play out, guys. So that was the work done for number 13. Work was 1.67 joules, or work is 5/3 joules, which is roughly 1.67 joules. For 14, see what we got here for 14, guys. All right, for 14, in regard to problem number 13, the one right behind me, guys, how fast is the object moving at x equals 30 meters? Here we go again. Let's say it one more time. For number 14, in regard to problem number 13 that we just did, right behind us, how fast is the object moving at x equals 30 meters? Good question. Well, all those joules of work went into kinetic energy. It's the same argument that we made in the past, you guys. The way this thing plays out is, let me see here, 14, okay. The change in the kinetic energy, well, initially it had no kinetic energy. It started at 0. The change in the kinetic energy is the amount of work that was done, because it wasn't climbing or anything like that. There's no climb taking place. It's on a frictionless surface, on a horizontal surface. And, or at least we're making that assumption. Let me see, did I actually say that? That's kind of Occam's razor. You can always ask me something like that. It did not say horizontal surface, but it is. It's, it's to be assumed, guys. Always ask if there's an issue. So it's equal to that. It started with 0 kinetic energy, and it went up to 1/2 mv squared. And all 1.67 joules went to that. Okay, well, let's see what we got here. It's a 2 kilogram object, right? It's 1/2 times 2 times v squared equals 1.67. 1/2 times 2 is 1. V squared equals 1.67. V squared equals 1.67, square root both sides, about 1.3. Yeah, looking good. Let's try number 15. Let's see here. Number 15. A machine does work, for number 15, a machine does work at a rate, the rate at which work is being done is called power, you guys, so be careful here. Number 15, a machine does work at a rate of P equals 50 e to the 0.1 t. From t equals 0 seconds to t equals 40 seconds. How much work did it do during that time? It's a classic integral problem. So what's going on here? What are they doing? What are they trying to say? So let me try to give myself a little room so I don't have to erase too much just yet. Well, let's just put it this way. I mean, if they're telling us that P is 50 e to the 0.1 t, that's what P is. That's power. And we're assuming all the units are well behaved. They're what they're quote unquote supposed to be. MKS system of units, System International, SI units, watts, joules, kilograms, newtons, meters, seconds, the whole thing. Okay, so we're pretty good. They're saying, okay, what was the work that was done? Well, this is the power. The power is based, power is a lot of ways to go here. Power is dW dt. The integral of power dt is integral dW dt dt, which is basically just the antiderivative, which is just going to be the integral dW, which is going to be W. Okay, so all right, that's well and good. So what's going on here? Going to run out of room here is what's going to happen. So let me try to build a little bit of room here. Okay, we did a number of things. So let's see here. Sorry, guys, I'm trying to build a little bit of room here. Great, I just erased. Oh, all right, well, I'll do it again, I guess, guys. Sorry about that. All right, let's try that again. Sorry about that. So basically, they've said a good amount. We said they're telling us P for power, is 50 e to the 0.1 t. That's P. P is dW dt. So if you integrate, which implies, I mean, of course, if you integrate power with respect to time, you are integrating power, dW dt, with respect to time. And that will give you just the integration of what dW is, and that'll give you W. Okay, well, we know that. If that's the case, that means all of this, and it'll get you W. You're going to integrate from 0 to 40. You're going to integrate from 0 to 40. 50 e to the 0.1 t dt. The antiderivative here is going to be, you got to get the function whose derivative will get you this. Well, here's how you do it. You take the 0.1 and go 1 over 0.1 times 50. 50 times 1 over 50, take the 0.1 and go 1 over 0.1. 50 times 1 over 0.1 is 500. 500 times e to the 0.1t. If you take its derivative, you end up getting 50 e to the 0.1t. 500 is the magic number here. So this time, and again, the way this goes is, there's easier and hard ways to do it and how comfortable you are with this. This happens here, and you get to here. Let's back up a second. If you want to call u 0.1 or 0.1, let's just stay consistent with what they're saying. 0.1t du dt is 0.1. du is 0.1 times dt. That means if you integrate 50 e to the 0.1t, you're integrating u. Du dt is 0.1 dt. That's du. You've got to undo the 0.1. So you write this. The whole process is basically, let's see how you want to take the whole process, I guess you could say. If you're going to write it like this, then you're basically talking about a situation where you're integrating 50 e to the u du. True. But didn't we say that du was 0.01 dt? So basically what you got here, if you could speak the language they're doing here, so you're I don't know, there's different ways this stuff gets said, I guess. You can write it as 50 e, this to me is the most intuitive. It may not be intuitive to everyone though this way. If they're saying this, tell you what I'm going to do. I'm going to put 0.1 dt right here. I'm going to put this guy still like this, and then I'm going to try to undo what I just did here by dividing by 0.1. All this means the same as that. Yeah, what's interesting there is this is 500. This is u, is the e to the u, and this is du. And when you do the integral, it's just e to the u. It's 500 e to the u, whereas the u is this, and that's where you get to here. To me, that's more intuitive when I look at it. You're looking at this thing right here about to play a game, and you're doing this. Well, yeah, do me a favor. Instead of dt, go 0.1 dt. Oh, you just did something here. Why don't you undo it? Why don't you divide by 0.1? They all cancel out, and it looks just like this. What was the point of all that? Well, this right here we said is du. This is u. This is 500. If you're integrating this, guys, and again, is not, I've written better, this is just e to the u times 500. That's 500 e to the 0.1t. And that's where you're getting this. So again, it's a little bit of a proof. Sometimes you want to look at it. Those of you not in a calculus-based class, this is not something you have to worry about. But those in the calc-based class, you need to worry about this and the non-calculus stuff. So you've got your challenge, but you got your challenge cut out for you, but you're going to do well. All right, so you got all that. We did all this. Let's see. Well, we've played this game in some way, in some form or another. We played a game like this a number of times. Here goes. You got 500. You got e to the 0.1 times t, that's 40 seconds that they're saying. E to the 0.1 times t. E to the 0.1 times t, t is 40. 0.1 times 40 is 4. That's e to the 4. That's not trivial. Then there's the other one. You pulled the 500 out of here, right? Here's the other one. 0 times this. Well, 0 in here, 0.1 times 0 is 0. E to the 0 is 1. All right, that's a little bit of a mess, but we got it. You play it. Play the game, you guys. What do we got going on here? From 0 seconds to 40 seconds, 26,800 joules. 26,800 joules. $26,800 joules, you guys, for number 15. Okay, how much work? Yeah, right, exactly. How much work did it do during that time? Remember, the machine does work at a rate of what we just said. P was whatever it was. P is the rate of work. That's dW dt, which we wrote over there. P is equal to dW dt. It's W divided by T for the non-calc, for the people not doing the calculus right now. W divided by T, for us right now, if you're, if we're doing a calculus-based preparation here, W divided by T, a more accurate way to say it is dW dt. P is W over T. More accurately, P is dW dt. dW divided by dt. So if P is dW dt, there it is. Why don't you integrate from t equals 0 to t equals 40 seconds? And we got, and here we did get our 26,000, we got 26,800 joules, which is, the 26,800 joules is 26.8 kilojoules. So that's how they're giving the answer, okay? 16. A 50-gram bullet moving horizontally with a speed of 700 meters per second strikes and passes through a 3-kilogram block moving with a speed of 5 meters per second in the opposite direction. One of the speeds has to be negative, guys. On a horizontal, in the opposite direction, on a horizontal frictionless surface. If the block is brought to rest by the collision, what is the kinetic energy of the bullet as it emerges from the block? Okay, there's a lot going on here. We'll take a look at it. Okay, let me just, I'll have that up there in a second, guys. Okay, guys, let's continue. For number 16, a 50-gram bullet moving horizontally with a speed of 700 meters per second. A 50-gram bullet moving horizontally with a speed of 700 meters per second strikes and passes through a 3-kilogram block moving with a speed of 5 meters per second in the opposite direction on a horizontal frictionless surface. If the block is brought to rest by the collision, what is the kinetic energy of the bullet as it emerges from the block? Okay. Momentum is conserved. Kinetic energy is not conserved, but momentum is. Kinetic energy is not necessarily conserved, whereas momentum always is. Momentum is conserved. Vector quantity. Watch out for the signs here, guys. We'll say the bullet is 50 grams, which is 0.05 kilograms. It's going at 700 meters per second. And the block is 3 kilograms, going at 5 meters per second in the opposite direction. So one's got to be positive, one's got to be negative. It doesn't matter, but you got to be consistent. And in the end, the block is brought to a dead stop, and the only thing moving is the bullet at some velocity v. The bullet is 0.05 going at some velocity v. I'm not talking about the block because the block's velocity after the collision is 0, so it's not in here. So you got this. So let's see what happens here. You kick the mathematics around a little bit, you guys, and you get this time, 0.05 times 700 is going to be 35. This times this is going to be negative 15. So it's positive 20 right here. And this right here is 0.05 V. Divide by 0.05 on each side, and you get 400 meters per second. That is how fast, that is the speed of the bullet as it emerges. So 400 meters per second. Sounds good. They want to know the kinetic energy. Well, here it's emerging at this speed. The kinetic energy is going to be 1/2 mass times velocity squared. Kinetic energy is going to be 1/2 the mass of the bullet, 400 squared. KE, it's an interesting problem in its own right. 400 squared is 160,000. 160,000, 1,600, 8,000, 4,000. I'm getting about 4,000 joules here at the end of this thing, if I kick around the math. And that's what they were asking. What's the KE at that point? Okay? 17. At time equals 0, a wheel rotating about a fixed axis at a constant angular acceleration has an angular velocity of 6 radians per second. 4 seconds later, it has turned through 300 radians. What is the angular acceleration of this wheel? So from t equals 0 seconds to t equals 4 seconds, it has turned through 300 radians. It has a constant angular acceleration of it has a constant angular acceleration. It has an angular velocity of 6 radians per second. So they're giving us a lot, and we can do a lot. See what we have here. So for 17, the analogy to the kinematics in the angular realm looks something like this. There is an analogy to this, obviously. They're analogous to each other. The d equals v sub I t plus 1/2 at squared. Well, instead of d, you put theta. Instead of v, you put omega. And instead of a, you put alpha. But otherwise, the other one looks like d equals v sub I t plus 1/2 at squared. This kinematic equation has this as an analogy. And we've talked about that. Let's keep going. Well, if this is the case, let's figure it out. It should be pretty straightforward at this point. If theta, got to keep it in radians now. If theta is 300 radians turned, initially the thing is going 6 radians per second. That's omega sub I. After 4 seconds, what happens? I don't know. We'll see. I don't know what alpha is, but I do know we're talking about 4 seconds right here. Everything's there except for alpha, and then we just do algebra to solve it. What we have here is 300. This times this is 24. 1/2 alpha this. Well, 4 squared is 16. 4 squared is 16. Half of 16 is 8. That's 8 alpha. Subtract 24 on each side. Right? So let's see here. If we're talking about this, you divide by 8 on each side. You're going to be 3 short. I'm trying to do some of this stuff in my head, I guess you could say. You're going to be 3 short of 300 divided by 8. And that's going to be 37.5, so it's going to be 34.5. Or is it? Yeah, it is. Okay, so we got it. Right there. So that's good for us. Let's keep going. 18. A mass M is connected as shown by a light cord to a mass big M, which is 30 kilograms, which slides on a frictionless horizontal surface. The system moves with acceleration a equals 3 meters per second. The pulley has moment of inertia I equals 0.3 kilograms times meters squared and rotates about a frictionless axle and has a radius, that axle has a radius of 0.1 meters. The cord does not slip on the pulley. What is the mass of M? This is a great question. Let's be careful. Let's look at it. Let's get it right. So what are they talking about? Well, there's a lot that can be said. Let's get some data down here. We're trying at the end of the day here for number 18. We're trying to find what M is, small m. Now we don't know. I mean, small m could be a very big number, bigger than big M. I mean, theoretically, it depends how the problem is set up and what's going on here. For our purposes, well, we don't know. So don't be too hung up on big M, big M, small m. But I wouldn't doubt if there's a good chance that small m is going to be a smaller number than big M. But that's not necessarily going to have to be the case. Let's talk about what we do know, and let's see what we can do. We don't know what small m is. Big M is 30 kilograms. Acceleration, the system moves with acceleration 3 meters per second per second. This is 30 kilograms. This is big M. Might not have made it big enough, I guess, but let's see if I can. All right. That's big M. Cross the bridge when we have to cross it, I guess. I is the moment of inertia. Radius is 0.1 meters. And we are trying to find small m. Let's see, we got just about everybody here. Yeah, okay. Try to find that. Okay. It's a lot there. Okay. A lot can be said. Basically, let's take a look at the torque and kind of play the game that way and see what we can say. I mean, there's some formulas that come to mind. I mean, you talk about, you got them in A is equal to alpha times big R. The torque, when two things are pulling against each other, I'm kind of putting the carriage in front of the horse on this one, guys. Let me draw it. And I'm going to assume which one's which on this one, I guess you could say. Pull in here, pull in there. Yeah, there's a lot of ways to write this. I didn't really draw it, so I'm going to have to kind of throw the dice on this one and draw it a little bit. Let me see here. Let me say a few things, and we'll take it from there. A is equal to alpha times r. A equals alpha times r, or alpha equals a over r. The one follows from the other. A equals alpha times r. A equals alpha times r, alpha equals a over r. We know that. If there are two opposing pulls, the one that wins the tug of war will win it by T2 minus T1. That's the resulting force. The resulting force applied on a circular object with a radius r. This is like the moment arm. That's capital R. Force times r is torque, and I times alpha is also torque. So that I times alpha is torque, and this is also associated with torque. So we've got that. We will say, I'm not saying too much beyond that. I'm going to say that there's more pull. You know, one pull, there's, well, I should draw it, I guess. See, one mass is a lot larger, I guess you could say. That's big M. Frictionless, but there's a moment of inertia on it, on the pulley, so be careful. That's small m, and we're trying to find that. You got this. So let's see here. We're assuming, well, there's a lot we're assuming here, actually. They're telling us the acceleration moves this way, and the acceleration for our purposes is downward. There's no way it can be anything other than that, guys. This is not going, if there's, in the absence of outside forces, this is not going to be moving to the left. And it's not going to move itself to the left unless there's a motor on it. I mean, for our purposes, they're just objects. And this is not going to move on its own to the left to move this up. This guy's going to pull them down. How massive is it? I don't know. But there's a pull this way, and there's a pull this way that's not as much. And that could be the T2 minus T1 that we're talking about. Okay, well, they're not really, I didn't really go there like that, but okay, good enough. Let's write a few things, and let's see where this thing wants to go. We know, as we said, there's a tug of war in the tensions. T2 wins it. That means this guy wins it. And the tug of war in the tension won by T2, this guy, that's the resultant force. Resultant force times moment arm is torque, and that's the same as I times alpha. Now, let's be careful. Can you write it like this? Is alpha the same as A over R? We just said that, way over there to the left. Therefore, multiply by big R on each side. And we got it in terms of A, because they gave us A. Now let's see what the heck that means. Well, I don't know. It could mean a lot of things. I don't know. I did what I did, and I almost regretted it as soon as I did it. But that's okay. We can play a lot of games with the mathematics. Why don't you divide by r squared instead? Divide by r squared on each side. It doesn't matter. These are all born of the same equation. You got a over r squared. Forgive me. Divide by r squared on each side. You got this. This thing right here let's do some math. I is 0.3, I is 0.3, R is 0.1, A is 3. 3 is A. A is 3. 3 divided by the quantity 0.1 squared. 0.1 squared is 0.01. 0.01 goes into 3. 3 divided, forgive me. Yeah, correct. No. This is 0.1. R is 0.1. Square it, it's 0.01. 3 divided by 0.01 is 300. 300 times 0.3 is 90. So this is kind of an interesting conclusion. It's not really a conclusion. It's a partial conclusion. We get to here. Now, T1 is this guy. T2 is that guy. T1, because of Newton's third law, is also here. T1 is the amount of force associated with this guy moving. This guy's big M, and it's moving at acceleration A, or with acceleration A. It's big M moving with acceleration A. Big M times A is what that tension has to be. So T1 is big M times A is 30 kilograms times 3 meters per second per second. T1 is 90 newtons. That's kind of neat. Therefore, T2 minus T1 equals 90, and you just told me that T1 was 90. T2 minus T1 is 90. T2 minus T1 is 90. Add 90 on each side. All right. We've drawn some conclusions. Drawn some interesting conclusions, you guys. We have T1 is 90 newtons. T2 is 180 newtons. Okay. If somebody's asking us questions, T1 is 90 newtons. T1 is 90 newtons. T1 is 90 newtons, and T2 is 180 newtons. All right, might be useful. What are we asking? I think what they're asking here is what's small m? What is the mass of small m on this one? So we've got that. So let me erase a couple things and figure out what we can say. Well, we said the way they play, Newton's third law is alive and well. If that's T1 this way, that's T1 that way. If this is T2 this way, it's T2 that way. T2 this way is the same as T2 that way. That's what we're going to use. We'll see. Let's see. Forgive me, guys. Let me fix that. Okay, if this is T1 this way, if this is T1 going to the left, it's T1 going to the right. If this is T2 going down, it's T2 going up. Okay, we already said that. And we didn't know what small m was, but we do know that I is 0.3. And look at the units. The units, we got to have the units straight, right? Kilograms meters squared. Yeah, it looks okay, guys, after I did whatever I did. All right, so let's, in our memory, as is this. So let's see. What is the mass of M? So, looking okay. Again, the stuff is sometimes easier done than said. Sometimes it's certainly not easy, but we know enough. I think we know enough, guys. The big thing is, if this is T2 pulling this way, this is also T2 pulling up. T2 pulling up, and this guy, there's a lot, well, yeah, that's true. T2 pulling up, we don't really have to go there. The big thing is, no, actually we do. If T2 pulls up like this, and this guy pulls down, who wins the tug of war? Well, we understood that this thing's going this way. The only way this thing can move, short of this thing having a motor on it, is this way, clockwise, and that's how it's going to fall. This guy wins the tug of war over the T2, which is pulling up. So let's figure out what we're doing here. So what we're saying is, we're saying that if you take the small mass, or small mg, minus T2, that slows it down, and its acceleration is still going to be a, and the net resulting force is going to be that. So this is really what gets us there. Well, if that's true, add a T2 on each side and subtract an MA. That's true. Yeah, I guess you can say that's true. So what? What else do you want to say? Well, there's a number of things you can say, I guess. If that's the case, I want to find small m. Let me divide by this quantity on each side. Divide the g minus a on each side. T2 is 180. This is 9.8 minus 3 is 6.8. Yeah, that's out of control. I mean, I probably could have done this in a much more efficient manner, but this is really the big move that you have to make, folks. That's the big move that you have to make. You have to make that move, guys. You say, okay, wait a minute. This guy's pulling really hard. This guy's trying to stop it, but can't pull as hard. The difference between the two is the resulting force, and that's small m times a. Well, we know what a is, but we don't know what small m is. Don't know what small m is, but we know what g is. We do know what t sub 2 is. We already solved it. If you do the mathematics right here, if it was 180 divided by 6, it'd be 30. If it was 180 divided by, by 7, it's something else. If it was 180 divided by 8, let's say, it would be 90 divided by 4, be 22.5. It's between 22.5 and 30 when you do the answer. Well, if you between 22.5 and 30, roughly speaking, the way I did it was, I said, let's say this 6.8 was an 8. 8 goes into here how many times? Well, it'd be like 180 over 8 is 90 over 4, is 45 over 2, is 22.5. Well, it's going to be bigger than 22.5 because this is smaller than 8. If it's a 6, it'd be 30. Well, it's going to be smaller than 30 because this is bigger than 6. It's between 22.5 and 30, you guys. Give yourself a ballpark idea of what's going on. And there it is. And there's your answer. That was, at the end of all this, that was 18. I managed to erase the number that we actually solved. All of this was 18. Well, believe it or not, 18, 19, and 20 are all tied together. So might as well kill a bunch of birds with one stone, I guess you could say. 18, 19, and 20 are tied together. So what we got here is 18, 19, and 20 all tied together, you guys. And so there we go. This was 18. So let's go right here and kind of get it together here, guys. This right here is 18. So 18 is small m is 26.5 kilograms. Okay. And again, we already, like I said, we already did that up here, but all right, what the heck? It's here. That's 18. 19 we already worked it out, 19 and 20. That's kind of the neat thing. That was 18. 19, in problem number 18 above, I think in previous exams, guys, I drew this up here and then I drew the actual items that were under consideration. So you're talking about, this guy right here being the T1, and this guy right here being the T2. It's probably not that legible to save its life, but there's the T1 is this guy, and the T2 is that guy. Okay. And in the past, I think it wasn't drawn on the exam, but it should have been. I think I drew it on the board when people were taking the exam. In problem 8, number 19, in problem number 18 above, what is the tension in the cord where big M is pulled? T1. So this is T1, where big M is pulled. So this guy right here is big M. What do they say? If it ain't broke, don't fix it, but I want to do it. Where big M is pulled, that's T1. Well, we discovered T1 is 90. And for 20, in problem number 18 above, what is the tension in the cord where small m is pulled? T2. That's 180. Forgive me, everything's written multiple times, I guess. Small m is 26.5 kilograms. We already solved that over there, so it's written down twice. Small m is 26.5 kilograms. T sub 1, the one that pulls big M, is 90 newtons. T sub 2, the one that is associated with small m, is 180 newtons. We already did that, I don't know how long ago, within the scope of having done this problem. Earlier, that was one of the earliest conclusions that we had drawn. So it already, if we wrote it down in our notes, bam, bam, we just write it down there and write it down again and we're good. Okay, not bad. So, if that wasn't enough, they kind of do it to us again. Let me see if I can keep some of this stuff up here so we don't have to rewrite all of it, but they do something similar here. For number 21, they've got a figure again. For number 21, a mass, small m, is 20 kilograms, is connected as shown by a light cord to a mass, big M, 35 kilograms, which slides on a frictionless horizontal surface. The pulley has moment of inertia, 0.3 kilograms. The pulley has moment of inertia, I, equals 0.3 kilograms meters squared, rotates about a frictionless axle, and has a radius, r equals 0.1 meters. The cord does not slip on the pulley. What is the magnitude of the acceleration of small m? The magnitude of the acceleration of small m is the same as the magnitude of the acceleration of big M. So that's kind of neat. Let's go ahead of the game here, man. Let's see where they're going to go with this. In problem 21 above, what is the tension in the cord where big M is pulled? T1. In problem 21 above, what is the tension in the cord where small m is pulled? T2. It's the same drawing, guys. Good, I guess. That's pretty good. Let's do it like that then. 21, 22, 23 is what it's going to look like. There's a lot there, and we're going to see it again. But that's all right. We're good. We're going to write down, let me see if I can use some of this business. Okay. 21, 22, 23. It's going to look, so there's some similarities here, kind of what we did earlier with the three-body problem, remember? 21, 22, 23. Let's fill in some of the blanks we got to do here, guys. There's a lot. You're going to see this again. I got a feeling, well, yeah, you're going to see a lot again, I think is what you're going to see. Let's get rid of some of this, but not all of this. And I'll just point it out as we go along, guys. Let's do this. All right. Let's play the game as they're telling us to. They're telling us mass small m is 20 kilograms. They told us that. They told us big M is 35 kilograms. This is for problems 21, 22, 23. They told us the pulley has moment of inertia 0.3 kilograms times meters squared. Yep, same thing we got. Rotates about a frictionless axle and has a radius of 0.1 meters. I got that too. What is the magnitude of the acceleration of that? They didn't tell us the acceleration. That's the one that's kind of blank right here. That's where we got it. Everything else okay. Yeah. Let's talk about it. let me see here, guys. I'm checking the... Okay, yeah, looking good. Okay, yeah, looking okay. So what we have here, well, let's play the game. They're still calling T1 what's associated with big M. They're still calling T2 what's associated with small m. There is a tug of war. The tug of war is won by T sub 2, so this thing undergoes an acceleration, and we got to find out the acceleration's this way, and the other guy's connected to it, so it's the same acceleration. It's going clockwise. T2 is associated with small m, T2 associated with small m, T1 associated with big M. So T1 this way also means T1 the other way, and T2 that way also means T2 that way. So T2 down and T2 up, Newton's third law. T2 down, T2 up, T1 to the left, T1 to the right, Newton's third law. So we've gone there, we know all this stuff. T2 wins it. There is a difference here, T2 minus T1 times R. The difference here is force. The difference here is a resultant force. The resultant force times the radius is the torque. And torque is I times alpha. We have all this. We know that alpha is A over R. We've said that, well, we said that somewhere, and I think, yeah, I did manage to erase it somewhere. We do know that, we know a lot of stuff. We know that torque is the difference between these two. That's the resultant force times R, the moment arm, and torque is also I times alpha. We also know that A equals alpha times R, which is the same as saying, alpha equals A over big R. Okay, we know that. We talked about that earlier. I ended up erasing it, of course, and at another time, but we have it here again. There's a lot we can say, but we better be pretty careful. There's a lot that we can say, and there's a lot that we don't know. So let's kind of deal with it. We know a good number of things. I wrote some stuff over there to the far left. You may want to ignore it for now, or maybe not. Let's take a look at the fact that this thing, that situation, has all the items. Everything's kind of moving, and I guess you could say if you want to put a clock on it, it's going clockwise. Big mass is going to the right, small mass is going down. They're both going with the same acceleration. Mass times acceleration is the resulting force. Well, mass times g is what it would be if you didn't have a cord attached to it, but this cord stops it somewhat, slows it down somewhat. mg minus t sub 2, that difference, mg minus t sub 2, is the resultant force, which is ma. From here, there's a lot of games you can play to get answers. We need to do a good amount of things to get this to happen. We need a lot here. We're trying to, we can't get away from, once we got this guy, we're going to know a lot. Maybe we'll know a lot before that. Like the last time, we ended up knowing a lot before that. But we got to get that guy. Well, see how we want to say this. There's a lot of ways. And I said a lot of stuff. It remains true. Let's come back a little bit. Said a lot of stuff. It remains true. We know that's true. It was true last time. We just need to know more stuff to make it happen. But let's see here. You got A right here. You got that whole business right there. And you also got, well, they say a bunch of things here. I'm trying to think of a good way to talk to you about it. I know this. There's a lot I got to know. Yeah, there's a lot I got to know. They told me a lot. They never told me the acceleration. but they told me R, they told me I, they did not tell me T1, they did not tell me T2. T1, T2, and A are all unknown. I need three equations. I need three independent equations in three unknowns. Well, this is one of them. Here's another one. This guy, T1 pulls M. T1 pulls with a force that's equal to the mass, big M, times acceleration. Here is a second equation. We have two independent equations in three unknowns. We need one more. Independent equation. I think we got it. We got this guy right here. I delivered this speech already. What T2 equals, right? And so you got it. You got T2. You can write this any one of these three ways, and in fact, there are different ways you can write this as well. How do you want to do this? I mean, we can do this a bunch of ways. I'm just kind of doing my own thing here. I'm going away from my notes a little bit and just trying to write it. T sub 2 equals M times the quantity G minus A. What kind of M are we talking? Small m, right? Right, it's the bottom guy. Well, here we go. Jackpot, guys. At least I think we're set. We can solve the three unknowns, which really are the questions 21, 22, 23. 21, 22, 23. They want A here, they want T sub 1 here, and they want T sub 2 here. A, T1, T2. That's where the three unknowns are associated with those three problems. These three equations are three independent equations. They're not derived from one another. These are three independent equations in three unknowns. And 21 will answer A. You get the answer. For 21, you want to find A. 22, you want to find T1. 23, you want to find T2. These three independent equations will give you A, T1, T2. It's about that simple. From there, it becomes an algebra problem. You can finish this long before I do it on the board. I'd be glad to do it on the board, and I'm going to. But let's figure out how we're gonna say all this. Trying to think how we're going to do this. We can definitely three equations and three unknowns, so that ain't a problem. I am incredibly tempted. Yeah, I think I got it. I mean, look, guys. I mean, you don't have to put numbers. I mean, the way you saw me do this in the past. I mean, this is number 1. This is number 2. This is number 3. Who cares who's 1, 2, or 3? Just there's 3 of them here. Here's number 3. Here's number 1. Here's 1. Okay. So let's think. I mean, I've done this in different ways. I'll figure it out. Here's the big thing. Once you find acceleration, you're done. Once you find acceleration, you already look for T2. Look at T2, for example. You already know what G is. It's 9.8. Once you find the acceleration, do the subtraction and multiply it by small m. Small m is 20 kilograms. That'll give you T2. Big M is 35 kilograms, and once you find A, you'll find T1. That's easy. Let's just find A. I got an idea. Let's look at this first one right up here. Let's put T1 equals big M times A. For T1 equals big M times A, put that right here. For T2 equals small m times the quantity G minus small a, put that there. Wheel and deal with it a bit. I is already given to us. R is given to us, so R squared is basically given to us. A is not given to us. We could set this up and have A's everywhere. Let's take a look at it. Let's see where this thing is going. Okay, so if that's the case, let's see where it goes. You saw me wheel and deal over here, guys, so you're okay. You can always go back. I always forget there's film here, and we can go back. T2 minus T1 equals I A over R squared. So T2 minus T1 A, forgive me. No, I should, yeah, the R's already out of there. T2 minus T1 is I times A over R squared. All right, here goes. Don't know what T2 is, but I know there's an equation for T2. It's number 3 over on the far right. That is mg minus A. So m is, maybe start putting in actual numbers here. T2, or maybe, yeah, not quite, but I'll do some of that. Let me just see where I want to go. T2 is m times the quantity g minus A. Small m is 20, g is 9.8, A is unknown. Okay. 20 times g minus A, which is 9.8 minus A. So it could get messy. Be careful, guys, when you do this. Let me write it like this. Maybe it makes it a little easier to look at. Minus big M times A. Well, big M is 35 times A. I is 0.3. A is unknown again. R is 0.1, and if you square it, you get 0.01. All right, let's think. Let's just think. Let's figure this. This is not bad. This isn't bad. 0.2. It's going to be 4 short of this. It's going to be 196. This is 196 minus 20A minus 35A. I don't know if I need to keep the brackets here now, but 0.01 into here is multiply this by 100. You got 30 times A. This isn't bad. If you wheel and deal with this, if you take 0.3, take 0.3 and divide it by, forgive me, yeah, right. Take 0.3 and divide it by 0.01, you get 30. 0.3 divided by 0.01 is 30. There's the A. Here we go. 196 minus 20A minus 35A is minus 55A. This is 30A. Add 55A. Add 55A on each side. Add 55A on each side. That's 85A equals 196. It's going to go in there more than twice. Divide by 85 on each side. It's going to go in there more than twice. Less than 2.5, though. Can't make this thing close to 2.5. Probably closer to 2.5 than it is to 2. Let's see what happens. Oh, about the same. I mean, A is 2.31. Okay, so let's have a look. Need a little more chalk, guys. Sorry about that. A is 2.31 meters per second per second. You got it. That's number 21. So, of course, I'm going to write it down again. It's going to look ridiculous. But okay, here's 21, guys. For number 21, A is 2.31 meters per second per second. We solved it. Let's just put it there, I guess. Let's put 22 and 23 over here. See if we can kind of make everything happen for us. 2.31 meters per, yeah, it goes in there more than twice. Does not go in 3 times, between 2 and 3 times. 2.5 would actually be too much as well, guys. It'd come out to 200, not quite, but it goes in there quite a few times. So we got 2.31 meters per second per second. Let's go. They want T1, I guess, right? T1 is big M times A. Well, we know what A is now. We've always known what big M is. Big M is 35 kilograms. 35 kilograms times 2.31, is 80 something. 80.7 newtons. So let's do it again. Big M, look over there. Look over there. Big M is 35 kilograms, and A is 2.31. 35 kilograms times 2.31 meters per second is 80.7 newtons. We got that. T1, 80.7 newtons. T2, yeah, well, here we go again. G is 9.8. A is 2.31. 9.8 minus 2.31 is 7.49, about 7.5. 7.49 times small m, which is 20, it's about 7.5 times 20, which is about 150. So it's going to be a little bit short of 150. Not much. Pretty close to it. 149.8 newtons. T1, T2, and there's A. That's everybody, guys. That's everybody. That's what we wanted. Notice that if you're doing this right, and you are going to be doing it right, when you're doing this right, guys, you're answering a lot more questions than the question that's being asked of you. And if they want to ask you more than that, you're more than ready to answer the question. So you got T sub 2. I'm sorry about that. When it smudges like that, it doesn't look as good. But all right. So it's looking all right, guys. But when like I said, when you're answering these questions, many things get answered. Usually when you're answering one of these questions, numerous questions get answered, some of which you're not being asked. You might be asked about them later on, and then you got 2 or 3 problems for which you already have the answer. In this case, a number of these cases, we already had 3 of these problems already solved for us just by adequately and accurately and very knowledgeably going through the procedures that we need to go through. Okay? That was 23. 24, 25. Let's just look at this, guys, really quickly, if you don't mind. I don't want to make a film and have it like up there and not be okay for us. All right, we're talking about 21, as we said. 21 was 2.31 meters per second squared. 22 was 80.7 newtons. 23 was 149.8 newtons. Okay, yeah, we're looking good. 24, 25, let's just go with some of the formulas that are already given to us or we've talked about. I may have given them to you folks. Sometimes I don't make you rederive it. If you derive the differential equations, many of these things come out. I mean, obviously, if you derive the differential equation, you know what you're actually doing. Let's take a look at it for 24 and 25. Start that out fresh, guys, in a second. Okay, folks, let's finish this up. Let's finish up exam number 2, the review for exam number 2. Exams 1, 2, and 3 will comprise the review for Physics 209, or if you're not in the Physics 209 class, it'll comprise some kind of a review associated with a calculus background when we are studying mechanics and heat. So, okay. Let's look at let's finish up exam number 2. 24 and 25 are what we're looking at. They are easier than they look, but be careful. For number 24, a rocket with an initial mass of 1,000 kilograms adjusts its thrust by varying the rate at which mass is ejected. The ejection speed relative to the rocket is 25 kilometers per second. If the acceleration of the rocket is to have a magnitude of 15 meters per second at an instant when it has lost 65% of its original mass, at what rate is mass being ejected at that instant? Ignore any external forces on the rocket. Okay, let's be careful. Let's you're looking at 65%. The question. The way it's phrased, perhaps, I mean, we have to train ourselves to see how the question is phrased. The actual solution is not too bad, but let's be careful here. 65% of the original mass has been lost. What does that mean? Well, if the rocket initially has 1,000 kilograms of mass and 65% of that has been lost, 65% of 1,000 is 650. 1,000 minus 650 is 350. 350 is what remains of the mass of the rocket. At that instant, let's see what's going on. Well, I'm going to go with this equation that we have derived in the past, that the book has also derived, and that we have derived. If you're looking at calculus, there are ways to look at that. If you're not looking at calculus, it looks very similar to that. Instead of dm dt, you have delta m over delta t. Instead of dvr dt, you have delta vr over delta t. That's about it. I mean, there's other things that come into play, but it's not too bad. So just be aware of that, how that could play out. The mass of the rocket, after 65% of its mass has been expelled, is 1,000, the original, minus 65% of 1,000, which is 650. You are trying to get dvr dt. You want an acceleration of 15. And we're going meters per second here. Meters, so I'm going to convert the 25 kilometers per second into 25,000 meters per second for the VE. And that is, I think I did not put the negative in there. It doesn't. We're looking for a magnitude at this point, so it's not imperative. And then you've got dm dt right here. Now they want to know the rate at which the mass is being expelled. They want to know that. Don't worry about the negative. That negative just tells you it's being expelled. So that's not a big deal, but technically there should be a negative right here. Divide by 25,000 on each side. And dm dt, divide by 25,000, that's a good question. You've got 350 times 15, 3,500 plus 1,750, 5,250 divided by 25,000. It's going to be kind of let's see, it's going to be a decimal point answer. So basically, you just divide by 25,000 on each side. This thing right here, let's say 350 times 15 is 3,500 plus 1,750. That's 5,250. 5,250 divided by this, it's a little more than 0.2. So that is believable. You've got 0.21 kilograms per second being expelled at that instant. At that instant. So there it is. That's 24. 25. A rocket moving in outer space maintains a constant acceleration, magnitude 25 meters per second, while ejecting fuel at a speed of 15 kilometers per second relative to the rocket. This is all, VE is relative to the rocket, you guys. Remember that. So let's read all this again. A rocket moving in outer space maintains a constant acceleration, magnitude 25 meters per second, while ejecting fuel at a speed of 12 kilometers per second relative to the rocket. Relative to the rocket. That's how the ejection of fuel is relative to the rocket. The speed they give you for the ejection of fuel is relative to the rocket. If the initial mass of the rocket is 4,000 kilograms, what is the magnitude of the thrust after 800 kilograms of fuel has been consumed, exhausted? Not as much as you, it's an easy problem. It's a relatively easy problem. The magnitude of the thrust is mass times acceleration. The magnitude of the thrust after 800 kilograms of fuel has been consumed, you've got to kind of look at it this way. The thrust is mass times acceleration, which is equal to, if 800 kilograms have been consumed, or expelled, or whatever, if they're not there anymore, you started out with 4,000 kilograms. What is the magnitude of the thrust after 800 kilograms of fuel has been consumed? Times the acceleration. They told us the acceleration was 25. Yeah. That's absolutely true. And that's, now what is that? Well, A is dVr dt. How fast is the rocket going? What is the acceleration of the rocket? That's this. Which is the same as, so that's this, which is the same as that. That's 3,200 times 25. That's, I would say 3,200, 8,000, that's 80,000, I think, when at the end of the day. You do all that, you knock it out, you got 80,000 newtons. We'll speak their language. If they're using kilonewtons, that's 80 kilonewtons. That's probably where they're going with the answers on that. All right, guys. We have thus far, and we'll do them all, eventually, but as I'm speaking to you now, we've done exams 1 and exams 2 pertaining to the 3-part review. We've done 2 parts of the 3-part review for the final exam associated with calc-based treatment of mechanics and heat. Many of the problems are useful for non-calc treatment physics and are advised for people. It's advised that people look at them. I'm leading for my students. All my students, all my students regarding mechanics and heat, whether they be taking a non-calculus based course or a calculus-based course, the films, the two sets of films for non-calc treatment of mechanics and heat and for the calc treatment of that same subject matter, there are two sets of 3 films regarding these things. For the non-calc, 3 films. For the calc-based, 3 films. I look at all 6, if you're in calc-based or if you're in non-calc-based. That's been the advice from the beginning of this. So this is exam number 2, and we'll talk soon. Take care.